Hi Bobcats. In this video we're going to take a look at how you write the formulas for compounds. This is something that is so fundamental to chemistry that even here in chapter 2, things like our homework platform are making the assumption that you understand what these formulas mean. So I just want to take a moment and take a look at this process. Our objectives for this lecture are to take a look at a chemical structure, and from that structure count the atoms and write a formula, but then also go backwards to look at a formula and understand how many atoms of any given element are indicated by that formula. I'd like to write the formulas for the two compounds that are shown here. They are each shown as molecular compounds, so after a certain number of atoms get clustered together, it's a closed unit and they don't attract any other atoms to be part of this unit. There's a fairly standard color coding when we're looking at structures like this. Generally speaking, red is going to indicate oxygen, white will indicate hydrogen, black will indicate carbon, and blue will indicate nitrogen. Other elements may or may not have standard colors, just kind of depending on who's doing the drawings. So this first molecule, the one that's on the left, has one oxygen atom and two hydrogens associated with it. We're going to indicate this by writing the symbols for each one of those elements, and we'll start with hydrogen in this example. So we'll write H for the hydrogen first, and then we'll write O, and that demonstrates that we have both the elements hydrogen and oxygen. And then to show that we have two of the hydrogens and just one of the oxygen, I'm going to put a subscript of 2 on hydrogen. So that subscript of 2 modifies the element that it comes after, so the hydrogen in this case. If there's only one of an atom, we don't indicate it with a 1, we just leave it blank. So a missing subscript means that there's 1. Just like when you write something like x versus x squared, when you write just plain x, it's understood that the exponent is a 1. For this element, for the second element, compound. For the compound on the right, there's one atom of carbon, so I'm going to write that as just a plain old C. And then there are 2 atoms of oxygen, so I'm going to write O2. So this is the compound carbon dioxide with 1 carbon and 2 oxygens. So the C goes with this black atom, and the O2 goes with the 2 red atoms. This molecule of caffeine is quite a bit more complicated. It has a lot more atoms to it. The atoms consist of carbon, hydrogen, oxygen, and nitrogen. I'm going to go ahead and write just those elements down here, right? We've got carbon, hydrogen, nitrogen, and oxygen. And right now, pause the video and count how many atoms of each type are here and list them as a subscript. All right, hopefully that was long enough. You paused the video, you got it all figured out. For carbon, in looking at the structure, there are 1, 2, 3, 4, 5, 6, 7, 8. It looks like there are 8 carbon atoms, so I'll put a subscript of 8 on the C. For hydrogen, I'm seeing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 hydrogen atoms. For the nitrogen, I'm seeing 4 of the blue spheres, so I'm going to call that 4. And for oxygen, I am seeing 2 reds, so we will just call that 2. Let's see. Okay, I think I got that formula correct. One thing I'd like to point out is that when a substance forms a molecule, like caffeine does, when we go to write the formula for it, we are going to leave the formula with subscripts that show exactly how many atoms of each type are in the molecule. If you look closely at all these subscripts, you can see that they all are even numbers, which means they could potentially be divided by 2 and keep the same ratio between elements. But for molecular compounds, we don't do that. We're going to write just exactly what atoms are present in one molecule. Sometimes we need to represent that we have more than one molecule of something present. So in this case, we've got 3 molecules of water. If I count up all of the atoms, I've got a grand total of 6 hydrogens, so H6, and 3 oxygens, O3. So based on what we just did, you might think that would be the best way to represent this. But when you write it this way, you lose the representation that a molecule of water is H2O, 2 hydrogens and 1 oxygen. So that's not what we actually do. Instead of writing the formula this way, we'll write H2O because that shows that we have that pattern of connected atoms. And then since there are 3 of these molecules, we'll put a coefficient of 3 out in front. And just to distinguish these numbers, the little one that we write down below is called a subscript, and the bigger number that we write out in front is called a coefficient. To count the atoms that are represented by this expression, what you would do is multiply the subscript times the coefficient. So 3 times 2 would give 6, and 3 times 1 would give 3. So we have 6 hydrogens and 3 oxygens. For this slide, please pause the video and take a moment to answer it, and then come back and we can answer it together. Okay, I hope you paused the video. To answer this question, how many hydrogens are in ibuprofen, C13H18O2? All we need to do is look at the formula itself, and the subscript of 18 modifies hydrogens. So this means that we have 18 hydrogens present in this expression. Once again, please pause this video and answer this question. All right, Bobcats, hopefully you paused it and you got this one figured out. We saw in the previous slide that a single molecule of ibuprofen has 18 hydrogens in it, but this expression indicates that we have 3 molecules. So to get the correct answer, we would multiply 3 times 18. And let's see, 3 times 8 would be 24, carry a 2, 3 times 1 is 3, plus 2 is 5. So there are 54 hydrogens in this expression, which would be the last answer. One of your homework problems also throws in a formula where something is written in parentheses like this. What this really is indicating is the formula for an ionic compound. And if we were to kind of sketch out what this looked like, you would have a calcium ion that has a +2 charge on it, and then you would have a nitrate ion, which looks something like this. And overall, this cluster of atoms has a -1 charge, and then that subscript of 2 that's outside of the parentheses means that there are 2 of those nitrate ions. I'll try to draw this one a little smaller. Cram it all in here. All right, so these are all of the atoms that are represented by this formula. And so if we're trying to count the atoms of nitrogen or oxygen, well, in looking at the diagram, there are 2 nitrogens. There is one here, and there is one here. So 2 nitrogens. In looking at the formula, I see a subscript of 1 on nitrogen, but outside the parentheses, there's a subscript of 2. So when you have subscripts, and parentheses. To find the number of something that's inside the parentheses, you multiply the subscript inside the parentheses times the subscript outside the parentheses. So if we're going to follow that pattern for nitrogen, it's going to be the 1 that's inside times the 2 that's outside, which means there are 2 nitrogens in there. For oxygen, there is a 3 inside times the 2 outside, which would give us 6 oxygens. We can verify that in our drawing. I'm going to use green to indicate the oxygens. We've got 1, 2, 3, 4, 5, 6 oxygens, so that checks. Wrapping up, let's go back to our objectives. We wanted to write the formula for a compound based on its structure, and we wanted to count the number of atoms of an element indicated by a given formula.